G'day. I got interested in RFID and NFC tags. I'm going to give a talk about this to the retired technophiles of Mainline meetup, and it's going to happen in April or May 2022. So this is just the start of the presentation I'm going to give to them. It's really, I'm just going through it here just to give an introduction to RFID and NFC. If you already know about it, then the second half of this is really where I was playing around with it and putting together some devices that use mainly NFC. So get into the presentation. What's RFID? So this is kind of the umbrella subject area. It's short for radio frequency ID. The technology was first proposed in about 1973. And the first real RFID patent came in 1983. That's at least when RFID was mentioned in a patent. And the basic idea is using radio or radio communications to communicate unique ID. There's at the RFID level, there's many implementations. You'll sort of see in here where there's many different ways, at least with the RFID specs, to implement this. And then we'll look at NFCs, which is a specific implementation of RFID technology. Going along the line of many different ways to implement RFID, you see there's many different frequencies that might be used, but kind of the typical ones that are used, low frequency, high frequency, and ultra high frequency bands, mostly publicly available bands to communicate. There's three main types of implementation for RFID, or the way RFID systems are put together. There's what's called PRAT, or passive reader active transponder. There's ARAT, where you have an active reader and an active transponder, and you might see this sort of thing where you want a longer range with RFID. Things like EasyPass, which is a tolling system in the US. When they time runners go in say a marathon, they use active reader, active transponder to get the range as runners go past a certain location in the race to identify them. And then kind of the one that you probably see more often is ARPT technologies, where it's active reader and passive transponder, and this is the one that has the lowest cost for the transponder because they don't have batteries and things like that. And this includes things like NFC tags on passports now. Most passports use RFID tags in them when you're inventorying things, so kind of when you see things in clothes shops and stuff. Usually that's using ARPT technology. And just a note there that with passive transponders, they don't have their own batteries, so they get powered over the air through the wireless power received from the active reader, and that's part of the reason they have much shorter range, because they need to be close enough to be able to get the power from the reader. RFID tags have at least a 4-byte unique ID. That's not super unique. Gives you probably millions or billions of combinations. But usually the first byte is used for the manufacturer ID of the tag. So you can't 100% guarantee at the RFID level for a 4-byte tag that you've got a completely unique tag. In most cases it's going to be unique. And the costs for RFID technology, because it's so simple, at least for passive tags, can be as low prices, say 4 cents a tag. But for some of the other implementations, like I said, for tolling and EasyPass, where you have an active transponder, you start looking at about $25 for the transponders in that case. Now looking at NFCs, and this is kind of where I'll look at most of the stuff in here. So that's a subset of RFID technology, and it has specialized and specific capabilities and follows more specialized and standards about how you implement it. And this is kind of the popular use of RFID, or the main one I'm going to be talking about in the rest of this video anyway. It always uses ARPT technology, so the idea of having an active reader and a passive transponder. The tags in this case, because they're passive, still low cost. They could be as cheap as 10 cents per tag, so that's a little bit more expensive than the most basic RFID tag could be, and that's mainly because of the overhead of the additional capabilities that NFC tags always have. NFC was standardized in 2003 with this ISO IEC standard, and there's a link here to the standard document. And it has these main capabilities. So it runs, NFCs run on the 13.56 megahertz band. There's something like a 20 centimeter max range with these, but a lot of tags have a lot shorter range than that. So more typically you'll see tags only have a range of 4 or 5 centimeters. They need to be close enough to the reader to be powered on, and they typically can transfer information at 106 to 424 kilobits per second. So it takes a little bit of time with a reader over a tag to read the information on them, depending on how much information is read. NFC tags have a locked unique ID. In this case, it's 7 bytes long, so much longer than just the basic RFID tag ID. So there's an example of one. So there's a lot of possible values for that. Again, the first byte is the manufacturer's ID, but you've still got billions and billions of different possible values. But that still doesn't mean that you're guaranteed that they're totally unique, but in most cases they will be. The nice thing about NFC is there's a lot of standards about how you format the data on a tag. So as well as having the ID, you can actually put different types of data onto the tag, and it's standards based. So what the data is and how you read it is all part of the standard. So you can encode things like URLs or URIs on the tag. You can put text on it, videos, mail information or mailing information, contact information, phone numbers, addresses, emergency information. So for example, you could have a tag that has information about typical emergency information. If you've got certain conditions, if there's certain drugs you're taking and things, there's a tag data format to specify that. There's a Bitcoin data format, and one interesting one is this Wi-Fi network tag. So you can specify on a tag how to connect to a network. So in fact, you could be walking into someone's house. If it has Wi-Fi information on the tag, you could automatically be logged into the guest network if you, say, wave your phone over that tag. And the other thing NFC has, which is used a lot, is the ability to selectively lock data on the tag. So you can write data to these tags, and you can also selectively lock that data so it can't be rewritten later on. So let's have a look at some of the typical formats. So for NFC tags, typically you see them looking like this, where this is a paper-based tag. So this is going to be the lowest price type of tag. So you see that they've got printed on the tag. The piece around the outside is the aerial, the wireless aerial, and how it gets power. And then in the center it has the chip that has the RF processing and the memory for the data that's encrypted on the tag. But you get other formats. So this is an example of a tag that's used for embedding under the skin. So it's typically these sort of things are used in animal and veterinary situations. So say for tagging cats and dogs. So if they get lost, you can find them again. This is typically what they look like. So they get injected under the skin to allow that to happen. You get a lot of different formats. So this is just some examples of different formats that a tag could be in. So things like business cards, key rings. A lot of times you get these tags where they have the use sort of printed as an icon on the front of them, so you know it's going to be a wireless one or a access one, all sorts of different tags. Another example of small tags that may fit in a wallet and be used for access to a building, say. Typically these paper tags come on a reel, so typically they get swiped onto inventory. So as you walk along, you just sort of swipe the tags off these rolls onto a whole bunch of boxes of inventory. Allows you to do a quick way to track inventory. And there's even more unique examples. Here's one example of where someone has created Lego compatible tags to go on Lego pieces, which could make for some interesting situations. So that's about it for the overview. So let's look at some specific implementations of using NFC tags. This is the PN532 board, which is a NFC RFID tag reader. Board came with a couple of RFID card and a RFID key fob and a couple of connectors. I'm going to use I2C, so I'm going to look to put the I2C connector into the I2C connector pins here. And also you have to change the switch here. I'll just show you how to do that under a high magnification, but basically you have to turn the switches on. So this is it on Amazon, the PN532 board, and here's a blow up looking at the little switch. There's a cover on the switch I had to pull off. It's kind of awkward with the tweezers, but managed to get the cover off. And then you can see below that I need to set the switches for the I2C, so the first switch needs to be set on and the second switch needs to be turned off. So we should be all ready for I2C now. And the other thing to do with the board is to solder the pins onto the I2C connectors on the board. After that, I used an ESP32 microcontroller. Has an OLED on it, so I can display the information on the OLED. Then I used Micropython to write some code to read, in this case, RFID tags. So you can see it going here. I put the RFID tag over the reader, and on the OLED I can see the tag ID. So these first two are a couple of RFID tags, about 4 digits long or 4 bytes long. If I use an NFC tag, it recognizes as such and shows the 7-byte ID. Now we've seen a demo of the Micropython code work, and I just wanted to run through the code a bit. So the first part of my code is got imports, and imports the SD1306, which is the standard way to talk to a OLED display. And this one's interesting, so let's have a little sidetrack to look at this PN53212C library. I'm using the Adafruit CircuitPython PN532 library to talk to the RFID card reader. This is a pretty well-made library. My only problem with it was it's written in for CircuitPython. I use the Micropython, so I had to do some conversions. So the actual libraries of interest are down here. So there's the base library that does all the smart stuff, and then there's these three wrappers for depending on how you're talking to the PN532, either through I2C, SPI, or UART interface. I'm just going to use I2C. These three libraries seem to have the most CircuitPython particular stuff because it's kind of close to the hardware label. So you'll see in the code where I've changed this around or modified it so it can work as a Micropython library. That's mainly what I had to do. The underlying Adafruit PN532 library, I didn't need to modify at all, so that makes it nice. I can drop in any updates to this and everything should still work. So carrying on through this code, a couple more imports. I set up the I2C bus. I also do a scan in here. I don't really need that for production, but it's nice to know what devices are tied to the I2C bus, and I'm always looking to make sure the OLED and the PN532 show up. Just initialize the SSD1306 object. That's my OLED, and just display some text just to make sure it's working at this point. Now I initialize a PN532 object, again just specifying what I2C bus I'm using. Also, if I specify the reset pin, it means the library will send a reset when it starts up to the reset pin on the PN532, and I found that needed to be done if I kept running the code over and over again without resetting the board. The board can sometimes be left in a uncommunicative position between one run and the next, so just making sure you hit the reset pin helps with that, and you'll see in the hardware diagram where I show where I use that reset pin. I just checked that the PN532 initialized correctly by showing the firmware version, so it should show that if it's been able to talk to the board. And then I go into a loop to keep checking to see whether there's any RFID or NFC tags put in front of the reader. So basically I'm using this read passive target, which is part of the library, to read if there's a UID present. I'm also keeping sort of last values as I go through, and this allows me to detect changes, so I'm not displaying information over and over again on the OLED. I only display it when a new UID or new tag is placed in front of the reader. Do some formatting of the data, and I display it both as output from the Micropython program, so you can see it on the console, and I also display it on the OLED, which you saw earlier in the demo. So that's about it for the code at the moment. So I'm going to have a look at using RFID tags with an iPhone. You can also use it with Android using a toolkit. The reason I'm doing that now is I want to put data onto the RFID card, or onto the NFC card actually. Things like URLs and things. And they'll be helpful when I come back to this code, because I want to still use this code to read the custom data, but until I get some data on the NFC tag, it'll be harder to debug this. So let's have a look at the iPhone NFC stuff, and then we'll come back to this code and show what I did to add the ability to be able to read the NFC cards. You can do some neat things with NFC tags on iPhones. I don't have an iPhone late enough to do this, but this is shown on my son's iPhone. So first way to use NFC tags is to use the shortcuts application. You can see it here, and this allows you to set up automations based on a lot of things, but in this case on an using an NFC tag, or seeing a certain NFC tag. So my son added a tag to his weights, and then he set up a automation so that a squat automation happens when he scans that tag, and this shows it going. So he scans the tag, and it fires up the health application on his iPhones, and he can enter details about what weights he's going to use. So shortcuts are just based on triggering based on a tag's unique ID. But another way is to actually write data to a NFC tag. So I'm going to use this NFC Tools application on an iPhone to write a URL to a tag. That makes it more generic. It can be run off any item. And I'm going to try doing some home automation with it. So to do this, I'm going to use NFC Tools. And I'll go through, and you can see here there's a whole lot of options of what you can write to an NFC tag. And then I'm going to fire off this process. So you can see in this diagram, basically I'm going to read the NFC tag, have the phone send the URL coded onto that NFC tag to a NodeRed script. They'll talk to AWS and Alexa will turn on a Hue light. Let's have a closer look at the script. So the NodeRed script is looking for a HTTP GET calling Alexa, which talks to a toggle node, and it switches between turning an Alexa node on and off. So now I've got the URL to write to. I'm going to bring up the NFC Toolkit, and I'm going to write that URL I created in NodeRed to the tag. So every time that tag gets scanned, it should send that URL to NodeRed, and then NodeRed will talk to Alexa and send a request to turn on the light. Keep going. Okay, and here's a demo of the whole thing working. So I scan my phone over the tag, click on the URL, and you see the light responded. Here's another example of a custom NFC tag. So I wanted a video tutorial associated with my oscilloscope. I went to YouTube and found a tutorial that I wanted to keep with my oscilloscope. And then I went into NFC Tools again. Same thing. I wanted to write the URL, but in this case it was the shortcut to the YouTube video I wanted to put on there. So I went to write a URL. And put in that YouTube shortcut. Wrote it out to the tag again. And let's have a look at it running. So there's my tag attached to the side of my oscilloscope. I can just run my phone up to that tag. I'll bring up the URL, I can click on it, and it opens the tutorial ready to go on my phone. Now that's kind of handy. And I could also put things like the manual for the oscilloscope on there as well. Okay, back to using the ESP32 and PN532 RFID card reader, and I want to find out more about how the various record types are formatted onto the card. So back in the program, so this was the big while loop we had before. Now I've got some cards that I've put some different record types onto the card so we can compare and have a look at what the data actually looks like. And the way I did that, so in this main loop again, when it sees a new UID, so basically seeing a new tag, it triggers it to go through this. And then if the UID is a length of 7, that tells me that the card is an NFC card. And the new function I'm using is this from the PN532 library, is this MyFair classic read block. So I read a whole bunch of blocks off the card. I think it's 179 bytes of data I read from the card, and just put it into this card data byte array. And then I pinch this piece of code. There's the link there to show that data in a Hex Dump. That all seems to work now. I've checked it into GitHub, so I'll put the link in the notes for this video on where you can get the code at this stage. And let's try running it. So let's upload it to the reader, and I'll try. I've got 3 different NFC cards with different data on it, so let's try that out. There's the first card that had the link to my home automation for the light on it, so I just had a simple URL. Let's try another one with the YouTube URL. And one more card where I haven't put anything on it, so really just showing what it looks like just with an empty card. There we go. So let's have a look at what this data tells us. So I found this article useful. It talks about NFCs and the NFC data exchange format called NDEF. Had a fairly good breakdown of what I should expect to find in dumps, and I also had some example dumps in here to allow me to follow along with. So let's have a look at my dump and see how this helps. Okay, let's have a look at the memory dumps. So the first dump here is for that third tag, which has no data on it. You can see here the first part of the memory has the unique ID for that tag repeated here, and then it gets interesting at position hex 13 in memory. So this is where what's called the TLV, or stands for tag length value field. It contains any data that's been written to the tag, and this one where hasn't been written, hasn't got much in there. So the first TLV field is 03, which is the tag and contains the type of field that's going to follow. So this, when it's an 03, that indicates that it's an NDEF field, which is a specification about data fields for a NDEF, for a NFC tag. The next field is the length of the TLV field, and it's 0. So it's saying that there's going to be 0 data in this field, and then it's got the TLV terminator character after that, FE. So again, very simple, and all zeros in the memory after that because it's a brand new tag. So let's look at a more interesting one. So this is the tag that I use for turning on and off that lamp. Uses the NodeRed Alexa routine. It's really containing a URL. You can kind of see it out here, but let's go through the same analysis of the data. So first bytes is the unique ID for the tag again, starting at position 13 hex. Has the TLV field definition. So again, this field type or field tag contains the field type saying 03. It's a NDEF tag, NDEF data in it. The next field is the total TLV length. So you can have multiple NDEF records in one TLV string of data. So this could be longer than this one record, which would indicate multiple records in here. And then the next field is the NDEF header. So we've specified 03, it's an NDEF record, so we'd be expecting an NDEF header at this point. And the important thing in there is it's saying that the NFC tag is a well-known type, as well as some other information about this particular NDEF data field. The next field after that is this 01, which is saying the NDEF type length. So you can have different types of NDEF records that define different things, so contacts, email addresses, URIs, which this one is, and they can have different lengths for that type field, but this is indicating that that type field is just 1 byte long, and the type field is this one here that's 55. But before that is the payload length here. So the payload length in this case is hex 19 bytes long, which is the length of the actual URL in this case. And like I said, the next byte after that is the 55, so this is the payload type. There's defined payload types, and 55 happens to indicate that's a URI is what the field type is for the NDEF record. After the 55, this is where the actual record starts, and part of the specification for URI fields is the first character indicates the URI prefix. So in this case, it's 03, and that means that the prefix is HTTP://. So it's just a way of shortening this URI. And there's multiple different prefixes you can define. So things like mail colon, HTTPS, all sorts of things. and then the actual rest of the URI field is here, and you can see it's 192.168.1.115, port 1880, which is my NodeRed port, and then the actual page that's been called is Alexa. So that's the memory dump, and again that Adafruit page has a really detailed analysis that I use for getting most of this information. Okay, finally I updated the Micropython code on my ESP32 so that it would send HTTP requests based on Signet tags. So first I just wanted to make sure that I could send HTTP requests. So first I had to set up the normal network configuration for ESP32. That's a little bit of code here where it connects to my guest network. Then otherwise, after the commented out Hex Dump part of it, I just do within a try block is call this MicroWebCli and do a GET request. So this is just sends a simple HTTP request using the Alexa lamp URL that I'd set up earlier. So that's the same old URL I've been using. I've put in a connect timeout of 3 seconds, so if it fails to get a response, it just does the accept and drops out of the loop. So let's have a look at that running. And again, this works no matter what tag I put there. So here's a demo showing that code working. So like I said, it's not looking for a particular tag ID or a particular tag at all. So it's going to send that Alexa command to turn my light on and off no matter what tag I use. So if I swap to a different tag, you see it's still working. Okay, this is the second set of changes I made to the code. So I had to change my ESP32 because it wasn't connecting to the network very well. I think the version of the ESP32 with the OLED on it has some network problems. It kind of hides the antenna under the rest of the stuff, so I changed to a separate ESP32, but to do that I had to change some of the pin assignments. So you see the new pin assignments for the I2C here, but otherwise much the same. And what I wanted to demonstrate here is where instead of sending the Alexa request to the lamp for every tag, this time it only does it on specific tag IDs, or a specific tag ID. So we should see a difference using different tags. So I'm going to use the tag that isn't for Alexa, so the ID is not recognized in this case. Now I'm going to use the Alexa tag, which has the ID that I coded into the program. And you see it turning on and off. So we're all good. Here's the most sophisticated version of the code. So in this case, I'm actually reading the NDEF tag that's been written to the NFC tag, and use the information on there to call a URL. So I had to add some constants here to identify different parts of both the TLV tag we saw in the when we looked at the memory dump, and the NDEF tag parts to identify as an NDEF tag for a URL. And then down in the actual code, and this is not the greatest way of doing it, but I then checked whether I saw the definition of the start of the TLV string like we saw before, using those constants. And then if I did, then I looked to see in the TLV block whether it's a well-known type, and the length of the type definition for the NDEF header this time, or NDEF type. And then I check whether the NDEF type is for a URI, so position 25. And if I've got all that, then I just check the memory location that tells me the length of the URL field in that NDEF record. After that, I look at the first character of the URL, and it uses shortening in all these URLs for NDEF. So I just included the first 4 choices, which include things like shortening it by removing http://www. And so on, you see down here. So I add that to the URL string, and then the second part I extract from the dump is the actual URL based on the length that we read up here. And then I just again call the MicroWebCli with a GET request, in this case for the S URL I extracted from the tag, and it either runs or it fails if it times out. So let's have a look at that running. So let's first try the Alexa tag that actually has the Alexa URL encoded on it. You can see that on the OLED as well. That worked. That turned the light on. Let's try another tag, which is the YouTube tag. And even though it has a URL, it doesn't change the light. Also, the empty tag doesn't change the light. If I use the Alexa one again, turns the light off. So it's all working. So that's about it for playing around with RFID and NFC tags. For me, it's a bit more interesting than I was expecting, especially doing the dump and finding out all about the standards around NFC tags, and playing around with Micropython and getting it working on a ESP32 was interesting as well. Hope you enjoyed it. That's it.